Okay, so in this video will be a continuation of my topology playlist, and I'll be talking about the cardinality of open balls. And we're gonna take a look at what happens when we try to draw open balls around a point in the integers, and what happens when we try to draw open balls around a point for the real numbers. And basically, remember our definition of open ball is that a ball is centered around a point C, such that X is a member of the set, and we're gonna say integers is our set for now, and the distance is less than some radius r. And remember that the distance is always dependent on the metric you choose. And so let's just get right into it. So let's suppose we have a point C, and we're going to draw an open ball around the point C minus r and then C plus r. It seems pretty straightforward. So we have our open ball there. And what if we wanted to draw another open ball inside this one? Well, we can always just go like this. Just draw one inside there, one inside there, one inside there. And this is I'm trying to make sure that I pass along an intuitive understanding of what's going on. So essentially, you can see that we can only fit a finite amount of open balls around this point, because here we have this is C minus r, and then this is C minus r plus 1, and this is of course C plus r minus 1. As you can see, the idea here is we can only fit a finite amount of open balls around this point C, and this is a property of any set that has a cardinality equal to the integers. And again, right here I'm assuming the Euclidean metric, because it's important that we specify which metric I'm using. The Euclidean metric is the one I'm using. So we can just keep drawing the point here, go all the way to the point C, and eventually we will not be able to draw any more open balls around a given point. That's interesting. But what if we do the same thing, and this time we have a point C, and here we have C minus r, C plus r, and what if we said that this time we wanted to draw an open ball, but instead of integers, we're going to take the reals, So let's say we start here and we start here. Well, remember, for the real numbers, there's an infinite amount of points between any two given integers. Let me just rephrase that actually. I'll say that for basically, if you have a point here and a point here, there's still an infinite amount of points between in this little region right here. And if you go like this and like this, if you make the interval even smaller, you will still have an infinite amount of points, because that's just the property of the reals. Remember, this is why the reals have a cardinality greater than that of the natural numbers, because you cannot, if you had a function that took the integers and mapped it to the reals, this would not be a bijection. It's not possible to make a bijection with the integers to the reals. And in general, if you have a set S, and you have mapping to another set, I guess R, if S is equal to the cardinality, the naturals, and the set R is equal to uncountable, is an uncountable set, then you will not be able to get a bijection out of them. And because you cannot get a bijection out of this, we can say that there's actually an infinite amount of open balls you can draw around the point C here. And actually, any point C you choose in the reals, you can draw an open ball around it. And that's interesting. And of course, the same thing would apply if we change R, we change it to something like like C and things like that. Any set that has the uncountable cardinals. And it's interesting because you can also extend this to n dimensions. Because of course here I just have I have the real line or the complex line, however whichever one you want to take a look at. But of course we can extend this to n dimensions, and this property holds, because the distance is defined for any set. Well, the Euclidean metric, I should say, is defined for Rn. Here we're just taking R, and all changes back to R, just consistent. So the Euclidean metric is defined for Rn, and so really you can apply this. The same property will hold for any dimension of the space. And so it's pretty much just a little note on the cardinality of the open balls. What can we do with them, and some interesting properties that countable versus uncountable sets have. And so the next video I'll actually be talking about exactly what a topology is, because in this video series I pretty much talked about a lot of concepts using topology, but I've yet to define exactly what a topology is. So that will be the next video. So I hope you guys enjoyed, and I'll see you then.